So let's think about this then. How do we go about getting somebody to VO2 max? So the image here is something that perhaps you may not have seen. So this is some work that we did a number of years ago where we were looking at oxygen consumption in equitational athletes. So this is on an Equisizer. This is a horse simulator. And you can see here we've got our a metabolic cart. We've got another device down here to record our cardiac output. And we've got our volume transducer, which is a little black object here. We're recording the O2 CO2 concentration, and it's all secured to the face through this face mask. That's one way of doing it. I'll show you some other ways in a moment. But when we are thinking about testing, whether it's on an Equisizer as you see here, or whether it's on a cycloergometer, in a swimming pool, on a treadmill, whatever the mode of test is, we have to think about these 6 important elements in terms of establishing a VO2 max protocol. First thing we need to think about is, well, what's the length of each increment? And you could see, particularly in the Astran data, that they were using 5-minute stages for each of their workload. Should it always be 5 minutes? Why is it 5 minutes? What about if I use a shorter stage duration? What about protocol duration? Does the length of the protocol overall or impact on the outcome? Is it important, for example? What's the rate of increase in resistance between those increments? So we saw on the Howley, Bassett and Welch paper that they went up by 2.5% every stage, and that they were holding the speed on their case at 7 miles per hour. We saw on the cycloergometer data sets from Astran and from Ferretti, both of those were using 50-watt increments. What should it be? What's the initial starting workload be? Because you can perhaps start to see how these are all interconnected. If I alter my starting workload, then fundamentally I'm going to perhaps, if I start at a very low workload, I'm going to increase the number of workloads somebody may need to do before they get to the point of finishing exhaustion. Does that matter? Does that have ramifications? If I start at a higher workload, I'm potentially going to reduce the number of workloads that they do. Does that have a ramification? And is that starting workload then connected to a protocol duration, if the protocol duration becomes important? Is that protocol duration linked to how long each stage should be? And is the length of each stage then connected to what the increment should be between each of those steps? So all of these fundamentally are interconnected. We then have to think about our ergometer type, and then finally how we're going to actually increase the resistance. Are we going to do what's called a ramp or a step? These are the most common ones, or perhaps what you sometimes see is linear. These are perhaps the most common ones. Are we stepping it or are we ramping it? So let's have a little think about these, because all of these have big ramifications. So here we've got a couple of examples of what happens when we change our protocol design. So these are kind of shown graphically, and these are based upon doing this where we've got on a treadmill in different examples. So what you can see in this example here is that we've got a constant gradient, and the gradient has been held, this is what this red line reflects, the gradient has been held here at 1%. So it's a constant gradient of 1%. But what's happened is the resistance has gone up, as we can see here, it's gone up by 1 kilometer an hour every minute. Okay. In this example below, what we've done is we've gone, okay, gradient's held at 1%, but the resistance is not going up every minute. You can see here that the resistance is going up. The resistance is going up every 3 minutes in this one. Let me explain why it's every 3 minutes. Although we've got the stage numbers here, it's going up every three minutes. And what you'll notice is, notice the steps are much bigger. So here we're starting at 9, now we're at 12, now we're at 15. So they're much bigger jumps. So fundamentally here, we've got smaller increments. So we've got to go from 10, so pretty close to what we've got here, 10, 11, 12, 13, 14, 15. I've got to go through all these stages to get to the same point here. And this has got a longer stage duration. These to here are where we are fundamentally holding the speed constant. So here the speed is held constant at 12 kilometers an hour, but now we're increasing the gradient by 1% every minute. Here we're increasing the gradient, but every 3 minutes, but the gradient increase is now, you see the gradient is going from 3% to 6% and so on. So why are these important? Well, first thing you'll notice is that the increments are much greater for these two down here, much bigger. So why is it that we're doing bigger increments compared to these smaller increments here? Well, this comes down to really fundamentally one of the key aspects that's often referred to is the duration that one should run a VO2 max test for. Now, the evidence for this was originally published back in the early 1980s by a German group, and they looked at some data. Admittedly, it was quite a limited data set, but they looked at some data and they really suggested from their data set that the kind of the window of opportunity to get what they perceived to be a both valid but also on a test retest scenario reliable outcome for a VO2 max test was between 8 to 12 minutes. Their argument was that if you've got less than an 8-minute total protocol, then actually what happens is the participant stops, not because they hit volitional exhaustion, that is not because they hit max cardiac output and max AVO2 difference, they stop because of some form of fatigue. Because if you're going to get somebody to max in less than 8 minutes, then the likelihood is that you're probably doing either very, very big increments, big steps, or you're doing lots of really tiny steps, but you're probably having to start at a much higher workload. So if you imagine that this participant here has hit VO2 max, and we've hit VO2 max at 20 kilometers an hour, but notice that we've done this in 11 minutes. So let's say I want to hit the window, which is an 8-minute test. So I would, rather than having to start them at 10, I would actually have to now start them at 12 kilometers an hour. That may not be a problem for this participant, but for other participants it may be. The other issue then is, well, okay, what about if I go for the, for the windows, the 8 to 12 minute window, which seems to be perhaps what is suggested. What about if I do bigger steps? I've got less variables here. Now, the problem with having less variables is that has a problem if we're trying to identify things like a plateau response at the end of the test. Because remember that each of these steps represents an increase in the VO2 response. So if we're suggesting that the participant is at VO2 max on this last stage, and I am taking an average VO2, as one would do if we're doing open circuit spirometry, and we're taking an average VO2 per each step, then the likelihood is that the VO2 is still going to be on the rise between these steps, these kind of longer 3-minute stages. That could be the 5-minute ones that Astran uses. So that becomes problematic. And in order to kind of fit our window of opportunity, the 8 to 12 minutes, we then have to have bigger steps. And that's why the step increments are much greater, because the argument here is trying to fit the 8 to 12 minutes. So all of these have that in common. Notice that kind of, if these are 3-minute stages, 3, 6, 9, 12, 3, 6, 9, 12, 15, slightly longer on this one, but still bigger increments. So this then poses an additional problem. If the increments are too steep, then one of the things that stops us is not exhaustion, is fatigue from having to either accelerate, because I've actually got to run a lot faster. I'm going from 10 kilometers an hour here to 9 kilometers an hour here to 12 kilometers an hour here. That might be beyond the capability of somebody because they're just having to accelerate. So the step increment has a big ramification. They stop because of fatigue, not because of exhaustion. So the design has to fit really within this kind of window of opportunity. Now that's been refined a little bit perhaps more recently. We tend to have a little bit of, be slightly more judicial on this, and we tend to go, right, okay, about 8 to 15 minutes. We've got a little bit of leeway of opportunity. If you are just interested in VO2 max, this is very different if you're trying to run this alongside collecting additional data such as blood lactate responses to get hold of lactate transitions, or you're looking at gas exchange thresholds. If you're doing a test that's covering more of those biological responses, then you really are looking at a minimum of 3 minutes per workload, but with much smaller increments, which changes the nature of the test somewhat. But if we are simply looking at this, perhaps more as a clinical measurement, where we perhaps just do VO2 max on its own, then the evidence really does seem to be smaller increments, because they are requiring less of a metabolic biological acceleration, but also allow us to fall within that window of opportunity, because I'm able to get more stages in if I start at a sensible workload to hit that kind of window of opportunity for 8 to 12 minutes. Now, if we then come a little bit further forward, so this is from some work from Todd Astorino's group, and this is related to perhaps the differences in using longer and shorter protocols in terms of the determination of VO2 max. Now, to a certain degree, this is a little bit misleading for us, because the notion of a long and short protocol in Todd's paper, which is a very, very good paper, is really kind of at those extremes, the 8 to 15 minutes. They're kind of calling a long protocol 15 and a short protocol 8. And actually what this sets out for us is, if we look at the average response here, this is the average response across all these individuals, there is almost no real effect in terms of the average VO2 max score between using an 8-minute protocol and a 15-minute protocol, which confirms that this is like that window of opportunity. But what it does show for us is there is considerable variability within participants. And so one of the things to think about is, well, why is the variability? Well, the variability seems to almost be related to the protocol that sits within that window. That is, how did we accelerate that person to VO2 max? Assuming we are going for across 8 to 15 minutes. What was the difference in terms of the protocol used and how somebody reacts to it? Some people may well react better to steeper increments. So, for example, you can see this participant here. Their score actually seems to be better when the stage duration must be either longer, or they're doing shorter increments but more stages, than what they've got here, where they are doing less work overall in the test. So you can see that the protocol duration certainly plays a part here. It doesn't necessarily have an effect on the overall max, but it certainly perhaps has to be taken into account when thinking about individuals, and we should always think of this in terms of the individual and their responses to the actual test. Now, if we come a stage further forward, one of the things to think about is the ergometer that you're going to use. So let's just park kind of the protocol design for the moment, but let's think about the ergometer. I think we're quite happy now in saying it's got to be in a window of probably 8 to 12 up to 15 minutes, that the protocol that you use, you're better off using shorter stages with smaller increments to really control the efficacy. But what about if we change the ergometer? So this is some data we published back in 2012, and what we took here was a group of relatively sedentary participants. You can tell they're relatively sedentary. You've only got to look at the VO2 max scores in the kind of the 40s if we take them on the cycle ergometer. And what we did was we compared those same individuals across ergometers, both on a test retest. That's why we've got cycling 1, cycling 2, treadmill 1 and treadmill 2, and also across ergometers. And what you'll notice is the choice of ergometer has an effect. These are not cyclists, these are not runners. And notice the difference. The VO2 max in the cycling is around about 43.8, average about 43.6 across these two. If we go to the treadmill, the average here, we've got a slight discrepancy between treadmill 1 and treadmill 2, but the average here is coming in at about 50.7 mils per kilogram per minute across the two. In other words, the VO2 max is actually quite a bit higher on the treadmill compared to the cycle ergometer. So the question is, well, why? And what is the relevancy of that? Well, of course, the simple answer to this, which I'm sure you're kind of thinking about, is it's related to the amount of active muscle mass that's engaged. On a cycle ergometer, the predominant muscle mass is that of the lower limbs. Remember that it's the lower limbs that are driving the force through the pedals. Whereas in treadmill exercise, it is much more associated with the whole body response. So the net result is that there would be a greater cardiac output because more muscles need to be perfused with oxygen. There's going to be a greater AVO2 difference because more oxygen's got to be extracted. So the net result is we would get a higher VO2 max on the treadmill compared to the cycle ergometer. So the question is then, well, actually, is this really a VO2 max here if it's higher here? And this is a really important point. VO2 max is ergometer specific. So yes, it is a VO2 max, assuming that they hit the criteria that we've been referring to, that is that we can see that plateau in VO2. That very much is the primary thing that one would be looking for. If the VO2 isn't leveling out, then it's very difficult to call that a VO2 max based response. But both of these represent VO2 max. They just happen to be ergometer specific. But it also lends itself to something which is really important, which is you have to pick an ergometer that is specific to the needs of the individual. So in clinical population groups, we tend to use cycloergometry because it is actually safer than using treadmill-based exercise, particularly in quite sick clinical population groups. Not to say that the treadmill's not without its merits, but if I was testing VO2 max in any population group, particularly clinical, I would have to use a safety harness when I'm pushing somebody to volitional exhaustion. I would absolutely encourage you always to use a safety harness when you're doing treadmill-based exercise. But if I'm testing a runner, then I would not test them on the cycloergometer, I'd test them on the treadmill because it's specific to the needs of their sport. The same with the cyclist would be on the bike, a rower on a rowing ergometer. And clearly one of the things that we understand is if I take a cyclist and I put them on the treadmill, despite the fact that they've got a greater active muscle mass on the treadmill, the VO2 max that they produce will be lower on the treadmill on the bike. And this is where you then get down to one of the key factors here, which is the mechanics of the movement. That they actually would become, as a cyclist, would become inefficient in terms of their responses. And actually what causes them to stop is the fatigue that they produce through the inefficient movements on the treadmill compared to on the bike. You would see the same if I transferred a runner to a cycloergometer. The inefficiency of the movement leads to the fatigue. It is the fatigue that stops the exercise, whereas what we want is the volitional exhaustion, which is the accumulation of fatigue.